Every object in the universe is spinning. The Earth beneath your feet is rotating at over 1,000 kilometers per hour. The Sun, despite its immense size, completes a turn roughly once a month. Galaxies wheel through space across timescales of hundreds of millions of years. Even atoms, the building blocks of all matter, carry a property called spin that behaves like rotation, but obeys rules unlike anything in everyday experience. This is not a coincidence. It is one of the deepest patterns in physics, and it raises a question that has occupied scientists for centuries. Why does everything spin? Where did all this motion come from? And why is it so difficult to find anything in the cosmos that sits perfectly still? The answer touches nearly every branch of physical science. It involves the collapse of gas clouds billions of years ago, the conservation laws that govern motion, the behavior of light and gravity, and the strange quantum properties that define matter at its smallest scales. It also touches on questions that remain unresolved, including whether the universe itself might be rotating in some way we have not yet measured. To understand why everything spins, we have to follow a thread that begins inside the atom and stretches outward to the largest structures ever observed. Along the way, we will encounter the work of astronomers, theorists, and experimentalists who have tried to make sense of a cosmos that refuses to stand still. What emerges is not a single explanation, but a layered story, one where many different mechanisms conspire to produce the spinning world we inhabit. And at the end of that story, a deeper mystery still waits. The first step in understanding cosmic rotation is recognizing just how universal it truly is. When astronomers turn their instruments toward any region of the sky, they find motion of a particular kind everywhere they look. Planets rotate on their axes while simultaneously orbiting their stars. Stars themselves spin while moving through their galaxies. Galaxies rotate around their central regions while drifting through clusters that may themselves possess slow rotational tendencies. Even the smallest objects studied in laboratories, including individual atoms and the particles inside them, exhibit behavior that physicists describe using the mathematics of rotation. There is no scale, from the subatomic to the intergalactic, where stillness is the rule. Motion of a turning, circling, revolving kind is woven into the fabric of physical reality. This observation alone would be remarkable, but it becomes far more striking when we consider how rare absolute rest is in nature. A simple thought experiment illustrates this. Imagine trying to construct an object that does not rotate in any sense. You would need to remove its orbital motion relative to any nearby gravitational source. You would need to halt any axial spin it possessed. You would need to suppress the quantum spin of every particle within it, which is impossible because that spin is intrinsic and cannot be turned off. You would need to isolate it from gravitational interactions with the surrounding cosmos, which is also impossible because gravity reaches across all distances. The conclusion is unavoidable. A genuinely non-rotating object cannot exist within the universe as we currently understand it. Rotation is not an exception or a special case. It is a default condition. The next question is whether this universality has a single cause or whether different forms of rotation arise from different processes. The answer turns out to be more nuanced than one might expect. At first glance, the spin of a galaxy seems to have little in common with the spin of an electron. The galaxy is a vast collection of stars and gas, held together by gravity and dark matter, while the electron is a fundamental particle whose behavior is governed by quantum mechanics. Yet, both are described by the same mathematical quantity, angular momentum. The fact that one equation can describe both extremes suggests that rotation, in some abstract sense, is a property that the universe applies broadly to objects of all kinds. To appreciate why this is so significant, it helps to consider how angular momentum was first identified as a fundamental concept. In the 17th century, Isaac Newton developed the laws of motion that bear his name, including the principle of inertia. An object in motion tends to remain in motion unless acted upon by an external force. This applied to straight-line motion in the simplest cases, but careful observers soon noticed that rotating objects obeyed an analogous rule. A spinning top continues to spin unless something slows it down. A planet in orbit continues to orbit unless something disturbs its trajectory. Over time, scientists realized that rotational motion possessed its own form of inertia, distinct from but parallel to the linear kind. This rotational inertia, when combined with how fast something rotates, produces the quantity we call angular momentum. The discovery that angular momentum is conserved transformed how scientists thought about the cosmos. Conservation laws are among the most powerful tools in physics because they allow predictions across vast scales and timescales. If angular momentum cannot be destroyed, only transferred, then any rotation observed today must have originated somewhere in the past. It cannot have appeared from nothing. This means that the spinning Earth, the spinning Sun, the spinning galaxies, all of them must trace their motion back through chains of cause and effect that extend across cosmic history. Some of those chains lead back to gas clouds that collapsed billions of years ago. Others lead back to gravitational encounters between massive objects. Still others lead back to processes in the early universe whose details remain debated. This conservation principle also explains why rotation, once started, is so difficult to stop. To slow a spinning object, one must transfer its angular momentum to something else. Friction can do this, but only in the presence of contact between surfaces. In the near vacuum of space, friction is extremely weak, which is why planets and stars maintain their rotation across billions of years with only gradual changes. Tidal forces can also transfer angular momentum as they do between Earth and Moon, but this is a slow process that operates across geological timescales. Magnetic interactions can play a role, particularly in young stars and in plasmas. Yet in most cases, an object that begins to spin continues to spin for an extremely long time, simply because there is no efficient way for it to give up its rotation. There is another reason that rotation is so widespread. When objects collapse under gravity, they tend to spin faster. This is a direct consequence of the conservation of angular momentum. If a large, slowly rotating cloud of gas contracts to a smaller size, its rate of rotation must increase to keep the total angular momentum constant. The classic analogy is a figure skater pulling in her arms during a spin, watching her rotation rate increase dramatically as her body becomes more compact. The same principle applies to gas clouds collapsing to form stars, to stars collapsing to form neutron stars or black holes, and to entire regions of the early universe contracting under their own gravity. Wherever matter pulls together, rotation tends to accelerate. This explains an important asymmetry in the cosmos. While there is no fundamental reason a particular gas cloud has to be rotating before it collapses, the slightest initial spin gets amplified during contraction. Even tiny rotational tendencies present in the original distribution of matter become significant when that matter is compressed into compact bodies. Over time, this amplification ensures that virtually every astronomical object ends up with substantial spin, regardless of how slowly it might have been rotating initially. The universe acts as a kind of rotation amplifier, turning faint asymmetries into prominent motions. The pattern goes further still. Once an object spins fast enough, it tends to flatten into a disk shape. This is because the outward effect of rotation balances against the inward pull of gravity differently along different directions. Along the axis of rotation, gravity is the only significant force, and material can fall freely toward the center. Perpendicular to the axis, in the equatorial plane, rotation resists further collapse. The result is that infalling material accumulates into a flat structure. This is why solar systems form with planets orbiting in roughly the same plane. It is why spiral galaxies appear as flattened disks of stars and gas. It is why accretion disks form around black holes and neutron stars. The disk geometry is a direct consequence of rotation combined with gravity. The implications of all this are profound. Rotation is not merely a feature of objects in the universe. It actively shapes how those objects form, how they evolve, and how they appear to observers. Without rotation, planets would be unable to retain their orbits in any organized way, galaxies would not have their characteristic structures, and stars would not undergo the convection patterns that drive their magnetic activity. The cosmos as we know it, with its hierarchies of orbiting and spinning bodies, exists because rotation is built into the basic physics of how matter behaves under gravity. As one possibility fades, another emerges. To go deeper, we must look more carefully at what rotation actually is, because the term means different things in different contexts. The word spin is used loosely in everyday language, but in physics it refers to several distinct phenomena that share mathematical similarities while remaining fundamentally different in origin. Untangling these forms of rotation is essential to understanding why the universe behaves as it does. There are, broadly speaking, three categories that physicists treat separately, even though all three contribute to the total angular momentum of any given system. The first is orbital motion, the second is axial rotation, and the third is quantum spin. Each obeys its own rules, arises from different causes, and produces different observable effects. Yet all three are unified by the same conservation law, which is part of why the concept of rotation is so powerful in physics. Orbital motion is perhaps the most intuitive of the three. When one object moves around another under the influence of gravity, it traces out a path that returns to roughly the same point over time. The moon orbits the Earth orbits the sun orbits the center of the Milky Way galaxy, and the Milky Way itself moves in complex paths within its local cluster. In each case, an object is moving through space along a curved trajectory, and this motion carries angular momentum, even though the object is not necessarily turning on itself. A planet in a perfectly circular orbit would have orbital angular momentum simply because it is moving in a circle around its star. The greater the mass, the greater the orbital speed, and the greater the distance from the central body, the more orbital angular momentum the system contains. This is the kind of rotation that dominates the dynamics of solar systems, star clusters, and galaxies. Axial rotation, by contrast, refers to the spinning of an object about an internal axis. The Earth rotates about its own axis once every 24 hours, producing day and night. The Sun rotates about its axis, although different parts rotate at slightly different rates because the Sun is not a solid body. Even stars spin, sometimes at extraordinary speeds. Some neutron stars, the compact remnants of massive stars that have exploded, rotate hundreds of times per second. This is axial rotation taken to extremes. The angular momentum of axial rotation depends on the mass distribution within the object, how that mass is arranged about the rotation axis, and how rapidly the object is turning. A dense, compact object that spins rapidly carries more rotational energy than a diffuse, slow one, even if both have the same total mass. The relationship between orbital and axial rotation is subtle. They are not the same thing, but they can be exchanged under certain circumstances. When tidal forces act between two bodies, angular momentum can flow from axial rotation into orbital motion, or in the reverse direction. This is happening right now between the Earth and the Moon. The Earth is slowing down in its axial rotation, while the Moon is moving outward in its orbit. The total angular momentum of the system remains the same, but it is being redistributed. This kind of exchange explains many features of planetary systems, including why the Moon always shows the same face to Earth, a state called tidal locking. The Moon long ago lost its independent axial rotation in the same way the Earth is slowly losing its today. The third form of rotation, quantum spin, is the most peculiar and the most resistant to ordinary intuition. Every fundamental particle in the universe possesses an intrinsic angular momentum that is not associated with any physical rotation in the ordinary sense. An electron has spin, but it is not actually rotating like a tiny ball. The mathematical description of its spin uses the same equations that describe rotation, but the underlying reality is something different. This intrinsic angular momentum comes in discrete amounts, multiples of a fundamental unit related to a quantity called the reduced Planck constant. Particles fall into two broad categories based on their spin values. Particles with half-integer spin, such as electrons, protons, and neutrons, are called fermions. Particles with integer spin, such as photons, are called bosons. The difference between these two categories has enormous consequences for how matter behaves. Fermions obey a rule called the exclusion principle, first articulated by Wolfgang Pauli. No two identical fermions can occupy the same quantum state simultaneously. This sounds abstract, but it has remarkable physical consequences. It is the reason that atoms have the structure they do, with electrons arranged in shells around the nucleus, rather than all collapsing into the lowest energy state. It is the reason that solid matter is rigid and resists compression, because the electrons in adjacent atoms cannot all crowd into the same region of space. It is also the reason that neutron stars and white dwarfs do not collapse further under their own gravity, because the fermions inside them resist being forced into the same quantum states. The entire architecture of matter, from the periodic table of elements to the existence of stable stellar remnants, depends on this property tied to particle spin. Bosons, by contrast, can pile into the same quantum state without limit. This allows phenomena like lasers, where many photons occupy the same state and produce coherent light, and superconductivity, where pairs of electrons effectively behave as bosons and flow without resistance. The bosonic nature of certain particles also underlies the transmission of forces, since the particles that carry the fundamental forces of nature are bosons. Photons carry electromagnetism, gluons carry the strong nuclear force, and certain heavy bosons carry the weak nuclear force. Without the distinct properties of bosons and fermions, the universe would lack both the structure of matter and the mechanisms that allow matter to interact. The fact that quantum spin obeys the same conservation law as classical rotation is itself a remarkable feature of physics. Angular momentum is conserved in any closed system, whether that system consists of planets orbiting a star or particles colliding inside an accelerator. This unification is not accidental. It arises from a deep mathematical relationship between symmetry and conservation, articulated most clearly in the early 20th century by the mathematician Emmy Noether. She showed that every continuous symmetry of nature corresponds to a conserved quantity. The conservation of angular momentum, she proved, follows from the fact that the laws of physics are the same regardless of orientation. If you rotate your laboratory in any direction, you should get the same experimental results. This rotational symmetry of space itself guarantees that angular momentum cannot vanish or appear from nothing. This realization gives the conservation of angular momentum a status that goes beyond a mere observational regularity. It is a logical consequence of one of the most basic features of physical law. As long as space behaves the same in every direction, angular momentum must be conserved. Any violation of conservation would imply a violation of rotational symmetry, which would be a far more radical departure from current physics than most people appreciate. This is why scientists take conservation of angular momentum so seriously. It is not just a useful rule. It is a structural feature of the universe tied to the very geometry of space. The implications run in both directions. If a system appears to lose angular momentum, then that angular momentum must have gone somewhere. If a system appears to have more angular momentum than expected, then that excess must have come from somewhere else. This forensic principle drives much of modern astrophysics. When astronomers see a star spinning more slowly than expected, they look for processes that could have carried away the missing rotation. When they see a system spinning faster than seems possible, they look for sources that could have supplied the additional rotation. The accounting must always balance, and that requirement guides scientific reasoning about objects that cannot be observed directly. Yet this evidence raises new scientific questions, because the origin of the angular momentum in the largest structures we see has never been fully traced. The conservation law tells us motion must come from somewhere, but to find that somewhere we have to look backward to the gas clouds that gave birth to the stars. The story of how stars and planets acquire their rotation begins long before any solid body exists. It begins in the vast clouds of gas and dust that drift between the stars, structures so large and so diffuse that they barely seem like material objects at all. These molecular clouds, as astronomers call them, span tens or hundreds of light years across. They contain mostly hydrogen, with smaller amounts of helium and traces of heavier elements left over from previous generations of stars. Their densities are extraordinarily low by terrestrial standards, with perhaps a few hundred molecules per cubic centimeter in their denser regions, compared to the trillions of molecules packed into the same volume of air on Earth. Yet these tenuous clouds are the cradles of every star that has ever formed in the galaxy, and the seeds of every planet that has ever orbited a star. What sets these clouds apart from empty space is their tendency to collapse. Gravity acts on every particle within them, pulling matter toward regions of slightly higher density. When the inward pull of gravity exceeds the outward pressures that keep the cloud expanded, a region begins to contract. This process can be triggered by various events. A nearby supernova might send a shock wave through a cloud, compressing it and initiating collapse. A passage through a spiral arm of the galaxy might increase local densities. Magnetic fields might gradually weaken and lose their ability to support the cloud against gravity. Whatever the trigger, once collapse begins in earnest, it tends to accelerate. As the cloud shrinks, its internal density rises, gravity becomes stronger, and the inward motion intensifies. But here is where rotation enters the picture in a decisive way. No molecular cloud is perfectly stationary or perfectly uniform. Each one possesses some net rotation, however slight, inherited from the turbulent motions of the interstellar medium. The cloud may appear nearly motionless when observed from outside, but in detail, its various parts are drifting in different directions, swirling at speeds that vary from place to place. When astronomers carefully measure the radial velocities of gas in a typical molecular cloud, they find that one side is approaching slightly while the other recedes, evidence that the cloud as a whole is rotating, even if extremely slowly. This rotation might amount to a single turn over millions of years, far too gradual to notice in any observation, lasting less than human lifetimes. Yet it is real, and it is critical to everything that follows. As the cloud contracts, this initial slow rotation becomes increasingly important. The conservation of angular momentum demands that as the size of the rotating system decreases, the rate of rotation must increase to compensate. A cloud spanning tens of light years that rotates once in a few million years might, when compressed to the scale of a forming solar system, rotate once every few years. When compressed further to the scale of a young star, the rotation rate increases again. The same principle that makes a figure skater spin faster. As she pulls in her arms, applies to gas clouds collapsing under gravity, but on a scale that dwarfs anything in human experience. A cloud that initially rotated almost imperceptibly can end up producing stars and planets that spin rapidly enough to flatten under their own rotational stresses. This amplification is not merely incidental. It governs the very structure of what emerges from the collapse. If a cloud had no rotation at all, it would collapse symmetrically toward its center, producing a single compact object with no surrounding disk. But because every realistic cloud has at least some rotation, the collapse is necessarily asymmetric. Material falling along the rotation axis encounters little resistance and falls inward freely. Material falling perpendicular to the axis in the equatorial plane encounters increasing rotational resistance and cannot reach the center directly. Instead, it accumulates into a flattened disk surrounding a central concentration. This is the protoplanetary disk, the structure from which planets eventually form. Every solar system that has ever existed began this way, with infalling material settling into a rotating disk around a young star. The geometry of this process explains a striking feature of our own solar system. The planets all orbit the Sun in roughly the same plane, called the ecliptic. They also orbit in the same direction, the direction inherited from the original rotation of the parent cloud. Some of the planets spin on their own axes in this same direction as well, although, as we will see, there are exceptions that demand special explanation. The overall pattern, with most rotations and orbits aligned, is a fossil record of the original collapse. By measuring these directions and rates, astronomers can reconstruct properties of a cloud that ceased to exist over 4.5 billion years ago. The motions we observe today are the preserved imprints of motions that began long before the Sun ignited. The same processes operate throughout the galaxy and throughout the observable universe. Wherever stars are forming, they are forming inside rotating disks. The youngest stars are surrounded by disks of gas and dust that are clearly visible in infrared and sub-millimeter observations. The Atacama Large Millimeter Array, an array of radio telescopes in the Chilean desert, has produced detailed images of these disks around distant young stars. The images show concentric rings and gaps, structures that suggest the formation of planets sweeping out their orbital paths through the surrounding material. Some of these systems are only a few 100,000 years old, mere infants on cosmic timescales, and they show conclusively that rotation organizes the formation process from the very beginning. The same disk geometry appears at much larger scales. Galaxies themselves form through a related process, with diffuse clouds of dark matter and gas collapsing over billions of years to produce the spiral structures we see today. The conservation of angular momentum applies just as rigorously at these enormous scales, ensuring that any initial rotation becomes amplified as the galactic scale material contracts. The flattened disks of spiral galaxies, with their stars and gas clouds organized into thin planes, are the result of the same physical principles that shape protoplanetary disks. The scales differ by many orders of magnitude, but the underlying mechanism is essentially the same. Gravity pulls inward, rotation resists in the equatorial plane, and the compromise produces a disk. There is something almost paradoxical about this. The initial conditions in a molecular cloud or a primordial gas region are extremely close to non-rotating. The cloud might have angular momentum, but the rotation rate is so slow that the cloud appears almost stationary on any reasonable timescale. Yet from these nearly motionless beginnings emerge stars and galaxies whose rotation is among the most prominent features of their existence. The amplification factor is enormous. A cloud that rotated once in a million years can become a star that rotates once a month, an increase in rotation rate of tens of millions of times. This is not magic. It is simply the inexorable consequence of contraction combined with conservation. Any rotation, no matter how slight, gets concentrated as material concentrates. The implications extend even further. Because amplification works on any initial rotation, the universe effectively guarantees that compact objects will be spinning rapidly. There is no realistic way to form a star or planet from a collapsing cloud without ending up with substantial rotation. Even cases that might seem like exceptions, such as slowly rotating stars, turn out to involve subsequent processes that slowed an originally faster rotation. The starting point is always significant spin, simply because contraction concentrates whatever angular momentum was initially present. This is why so many observations of stellar systems show rapid rotation, especially in young stars that have not had time for braking mechanisms to act. The youngest stars in nearby star-forming regions sometimes complete a full rotation in less than a day, a rate that no terrestrial intuition would predict. Once these stars settle into stable existence, their rotation continues to influence them in many ways. The rotation drives magnetic activity, generates winds that flow out through interplanetary space, and shapes the structure of any surrounding planetary system. The disk that gave birth to the star slowly disperses, with some material forming planets, some falling back onto the star, and some being driven away by radiation and winds. What remains is a star at the center, a system of planets in roughly aligned orbits, and a residual angular momentum distribution that reflects the original collapse. The pattern, repeated countless times across the galaxy, is the standard story of stellar birth. And nowhere is this pattern more visible than in the local solar system, where the consequences of that ancient collapse continue to shape conditions on a planet whose rotation gives rise to day and night. The Earth rotates on its axis once approximately every 24 hours, a rhythm so familiar that it defines the basic structure of human life. Yet that rotation, taken for granted in everyday experience, is a complex phenomenon with a long history and an uncertain future. Understanding why the Earth spins, how fast it spins now, how fast it spun in the past, and how that spin is changing requires reaching back through the entire history of the planet and forward into the deep future. The story involves the same molecular cloud collapse described earlier, but it also involves catastrophic impacts, tidal interactions, internal friction, and even effects from distant celestial bodies. The rotation of our planet is not a simple constant, but a slowly evolving feature of a dynamic system. The original spin of the Earth was inherited from the protoplanetary disk that surrounded the young sun. As small bodies in that disk collided and merged to form larger objects, they brought their orbital and rotational angular momentum together. The growing Earth accumulated mass from many directions, but the net effect of all those collisions produced a body with substantial axial rotation. By the time the Earth had reached something close to its current size, roughly 4.5 billion years ago, it was spinning much faster than it does today. Some calculations suggest that the early Earth completed a full rotation in as little as 6 hours, though the precise figure remains uncertain. A day on the young Earth would have flashed by at a pace that no living thing today could comfortably endure. What happened next was a catastrophic event whose consequences shaped the planet to this day. A Mars-sized body, given the name Theia by researchers, collided with the young Earth in a glancing impact. The energies involved were staggering, sufficient to melt large portions of both bodies and to eject enormous quantities of material into orbit around the surviving Earth. From this orbiting debris, the Moon eventually coalesced. The impact also altered the Earth's rotation, tilting its axis to its current angle of about 23.5 degrees from the perpendicular to its orbital plane. This tilt, along with the rotation that survived the collision, set the stage for the seasonal cycles that have governed climate ever since. In the aftermath of the formation of the Moon, the Earth-Moon system began the long process of tidal interaction that continues today. The Moon raises tides on the Earth, primarily in the oceans, but also to a smaller extent in the solid body of the planet itself. Because the Earth rotates faster than the Moon orbits, these tidal bulges are carried slightly ahead of the line connecting the two bodies. The gravitational attraction between the Moon and these displaced bulges produces a torque, a turning force, that slows the Earth's rotation while simultaneously pushing the Moon outward in its orbit. Angular momentum is transferred from one body to the other, but the total angular momentum of the system is preserved. The Earth gives up rotation, and the Moon gains orbital energy. This process operates extremely slowly by human standards, but adds up over geological time. Measurements using laser ranging from the Earth to retroreflectors left on the lunar surface by Apollo astronauts in Soviet missions show that the Moon is currently receding from the Earth at a rate of about 3.8 centimeters per year. In the same period, the length of the Earth's day is increasing by a few milliseconds per century. These rates seem trivial, but multiplied over hundreds of millions of years, they produce dramatic changes. Paleontological evidence supports this picture. Fossil corals from the Devonian period, roughly 400 million years ago, show daily and annual growth bands. Counting these bands suggests that a year in that era contained about 400 days, each shorter than today, consistent with a faster rotating Earth. The picture extends further back still. Banded iron formations, sedimentary structures laid down billions of years ago, preserve evidence of tidal cycles that have been used to estimate ancient rotation rates. The conclusions vary depending on the methodology, but the overall trend is consistent. The Earth has been slowing down throughout its history, and the Moon has been steadily receding. Models that combine these measurements with theoretical understanding of tidal physics produce reconstructions of the planet's past rotation that, while imperfect, give a coherent picture. The young Earth spun rapidly. The middle-aged Earth spun moderately fast. The present-day Earth spins at a pace that allows the development of complex weather systems and stable seasonal patterns. But the trend towards slower rotation continues. This trend has important consequences. The current length of day is not a fixed feature of the planet, but a snapshot taken at a particular moment in its long history. If humans had evolved on a faster rotating Earth, the rhythms of life would be entirely different. Conversely, if we lived in a future when the day had stretched to 40 or 50 hours, the climate and biology of the planet would be transformed. The slow tidal breaking is one of the major drivers of long-term change in the Earth's environment, operating quietly in the background while life unfolds across the surface. The Earth's rotation also influences far more than just the cycle of day and night. The spin of the planet, combined with its near-spherical shape, produces what scientists call the Coriolis effect. Moving objects on a rotating sphere appear to follow curved paths when viewed from the rotating frame of reference. This deflection is responsible for the rotation of large weather systems, including hurricanes and other cyclones. In the northern hemisphere, large-scale air masses rotate counterclockwise around low-pressure systems, while in the southern hemisphere they rotate clockwise. Ocean currents follow similar patterns. The atmospheric jet streams that influence weather across continents are themselves driven by the combination of solar heating and the Earth's rotation. Without the spin, these patterns would not exist, and the climate of the planet would be unrecognizable. The rotation also generates the centrifugal effect that makes the Earth slightly ablate. The planet bulges outward at the equator and is flattened at the poles, with the equatorial diameter being about 43 kilometers larger than the polar diameter. This deformation is a direct consequence of rotation, acting on a body that is large enough to behave plastically over long timescales. The same effect, more extreme in faster rotating bodies, produces noticeable flattening in planets like Jupiter and Saturn, where the equatorial bulge is much more pronounced. On Earth, the bulge influences satellite orbits, the local strength of gravity, and even the shape of the geoid that defines mean sea level. Internal processes within the Earth also tie into its rotation. The molten outer core of the planet, composed mostly of iron and nickel, flows in patterns that are influenced by the planet's spin. These flows generate the Earth's magnetic field through what is called the geodynamo, a self-sustaining process in which moving conductive fluid creates electromagnetic effects that reinforce the very motion producing them. Without rotation, no geodynamo would exist, and the Earth would have no global magnetic field. The absence of such a field would expose the surface to far more cosmic radiation and solar wind, with potentially severe consequences for the development and persistence of life. The magnetic field, generated by rotation and convection deep within the planet, has shielded the biosphere across billions of years. Subtle variations in the Earth's rotation rate occur on shorter timescales as well. The planet does not rotate at a perfectly constant rate. Seasonal variations, driven by the redistribution of atmospheric and oceanic mass, produce changes of milliseconds in the length of day across the course of a year. Earthquakes can produce abrupt but tiny changes by redistributing mass within the planet. The melting of ice sheets and the consequent rise in sea level slightly alter the planet's moment of inertia, with measurable effects on rotation rate. Even the movement of groundwater across continents can produce detectable signatures. Modern atomic clocks and very long baseline interferometry have made it possible to track these variations with extreme precision, revealing the Earth as a dynamic body whose rotation responds to many influences simultaneously. Looking forward, the trend towards slower rotation will continue. Eventually, in tens of billions of years, if no other process intervenes, the Earth would become tidally locked to the Moon, just as the Moon is already tidally locked to the Earth. The same hemisphere of the planet would always face the Moon, and the day and the month would become equal in length. In practice, this future state will not be reached because the Sun will have evolved into a red giant long before then, transforming conditions on Earth far more drastically than tidal forces ever could. Yet the principle illustrates how rotation, once thought of as a fixed property of a planet, is actually a slowly changing feature of a coupled system. The Earth's spin is the result of its formation, the history of its interactions, and the ongoing processes that continue to redistribute angular momentum between it and its surroundings. And nowhere is that interaction more visible than in the relationship with the very satellite whose orbit has been the principal cause of the Earth's slowing rotation across billions of years. The Moon is the most familiar object in the night sky, yet its relationship with the Earth is far more intricate than casual observation suggests. The two bodies form a coupled system whose dynamics have been shaped by mutual influence over billions of years. The moon does not simply hang in space, decorating the night sky and producing tides. It is an active participant in the ongoing evolution of the Earth, transferring angular momentum, stabilizing the planetary axis, and slowly transforming the rhythms of its larger companion. To understand this relationship, it helps to look closely at how tidal forces actually operate, because the principles involved illuminate similar processes occurring throughout the universe. Tidal forces arise because gravity weakens with distance. The moon pulls on every part of the Earth, but it pulls more strongly on the side facing it than on the side facing away. The result is a slight stretching of the Earth along the line connecting it to the moon. This stretching is most visible in the oceans, where water can flow freely in response to the differential pull. Two bulges form, one on the side of the Earth facing the moon and one on the opposite side. As the Earth rotates beneath these bulges, the oceans rise and fall in the familiar pattern of tides. The same effect occurs in the solid body of the Earth, although the response is much smaller, because rock does not flow as readily as water. Even so, measurements show that the solid Earth distorts by several centimeters under the influence of lunar tides, with continents rising and falling on a daily cycle. The geometry of these tidal bulges turns out to be crucial. If the Earth were not rotating, the bulges would align perfectly with the direction to the moon. But because the Earth rotates faster than the moon orbits, friction between the moving oceans and the underlying seabed drags the bulges slightly ahead of the line to the moon. This displacement is small, only a few degrees, but its consequences are profound. The displaced bulges have mass, and the moon's gravity acts on this mass. Because the bulges are not directly under the moon pulls on them in a way that produces a torque on the Earth, gradually slowing its rotation. Simultaneously, the displaced bulges pull on the moon in a direction that has a forward component along its orbit, accelerating it slightly and pushing it into a higher, slower orbit. This exchange of angular momentum is invisible in everyday experience, but has been measured with extraordinary precision. The Apollo missions left retroreflector arrays on the lunar surface, mirrors designed to bounce laser pulses back to Earth. By measuring the time it takes for a laser pulse to travel from a terrestrial observatory to the moon and back, scientists can determine the Earth-Moon distance to within a few millimeters. Decades of such measurements have established with great confidence that the moon is moving away from the Earth at a rate of about 3.8 centimeters per year. Although this might seem trivial, it represents enormous energy and angular momentum flowing through the system over geological time. The implications for the past are striking. If the moon has been receding throughout history, then in the distant past it was much closer to the Earth. Calculations suggest that in the earliest period after its formation, the moon may have been only a fraction of its current distance from the Earth, perhaps as close as 20 or 30,000 kilometers, compared to the current average of about 384,000 kilometers. At such a close range, the moon would have appeared enormous in the sky, perhaps 15 or 20 times its present apparent size. The tides it raised would have been correspondingly more dramatic, with ocean tides on the early Earth reaching heights that no modern shoreline experiences. The combination of a faster rotating Earth and a closer moon produced a tidal environment unlike anything seen today. These conditions may have played a role in the origin and early evolution of life. Some researchers have proposed that the strong tidal cycles of the early Earth created repeating cycles of wetting and drying along coastlines, which could have concentrated organic molecules and facilitated the chemical processes that led to the first self-replicating systems. While this remains speculative, it illustrates how the long history of tidal interaction may have left imprints not only on the physical configuration of the planet, but also on the conditions under which life began. The slow recession of the moon has thus been more than a curiosity. It has been part of the environmental context within which terrestrial biology has unfolded. The moon, for its part, did not always show the same face to the Earth. In its earliest period, the moon rotated more rapidly on its own axis than it orbited the Earth. But the same tidal mechanism that is now slowly slowing the Earth operated much more efficiently on the smaller moon, because the Earth raises far larger tides on the Moon than the Moon raises on the Earth. Over time, these tides break the Moon's rotation until its rotational period exactly matched its orbital period. This state, called synchronous rotation or tidal locking, means that the same hemisphere of the Moon always faces the Earth. The far side of the Moon was completely unknown to humans until the Soviet spacecraft Luna 3 photographed it in 1959, more than 3 centuries after the invention of the telescope. Tidal locking is not unique to the Moon. It is the natural end state of any tidal interaction given sufficient time. Many moons of the outer planets are tidally locked to their parent worlds. Some of the closer orbiting exoplanets discovered around other stars are believed to be tidally locked, with one hemisphere permanently facing the star and the other permanently in darkness. Such configurations would produce extreme climates, with the day side baking under perpetual sunlight and the night side frozen under perpetual darkness, although atmospheric circulation could moderate these extremes. The principles governing these distant worlds are the same as those that locked the Moon long ago. The Moon plays another role in the stability of the Earth that deserves emphasis. The rotational axis of the Earth is tilted at about 23.5 degrees relative to the perpendicular of its orbital plane, and this tilt is responsible for the seasons. Without external influences, the orientation of this axis would wander significantly over time due to the gravitational tugs of the Sun, the other planets, and the irregular distribution of mass within the Earth. Computer simulations suggest that for a planet like Earth without a large moon, the rotational axis could swing through angles ranging from nearly 0 to perhaps 60 or 70 degrees over timescales of millions of years. Such variations would produce dramatic shifts in climate, with poles sometimes lying directly under the Sun and equatorial regions sometimes plunged into long darkness. The Moon prevents these large excursions. Its gravitational influence, combined with its substantial mass relative to the Earth, provides a stabilizing effect that limits the wobble of the planetary axis. The result is that the Earth's axial tilt has varied only between about 22 and 24.5 degrees over the past several million years, a relatively narrow range that has allowed the climate to remain within parameters compatible with the persistence of complex life. The Moon, in this sense, is not just a tidal partner but also a climatic anchor holding the planet steady against forces that would otherwise produce chaotic variations. Mars provides an instructive contrast. The 2 small moons of Mars, Phobos and Deimos, are far too small to stabilize the rotational axis of their planet. As a result, the obliquity of Mars varies dramatically over geological timescales, swinging through angles that have produced very different climates in the planet's past. Evidence on the Martian surface, including features that suggest the past presence of liquid water in regions where it could not exist today, may be related to these obliquity variations. What Earth experiences as climatic stability, Mars experiences as climatic chaos, and the difference is largely traceable to the presence or absence of a large, stabilizing satellite. The future of the Earth-Moon system continues the trends already established. The Moon will continue to recede, slowly, for as long as the tidal mechanism operates. The Earth's day will continue to lengthen, also slowly. The eventual outcome, in the absence of other factors, would be a state in which the Earth's rotation has slowed to match the Moon's orbital period, and the 2 bodies would be mutually tidally locked, always showing the same hemispheres to each other. This state would imply a day many times longer than the current 24 hours, perhaps as much as 50 days, and a moon much farther away than it is now. Whether such a state would actually be reached depends on the evolution of the Sun, which will eventually expand into a red giant phase and engulf or destabilize the inner planets long before the tidal equilibrium could be achieved. The Moon and Earth, in the very long term, are bound to the fate of the larger system within which they orbit, and the rotation of the central body of that system, the Sun itself, follows different rules that reveal the strange behavior of a body composed entirely of plasma. The Sun rotates, but not in the way a solid body does. Because it is composed entirely of plasma, hot ionized gas with no rigid structure, different parts of its surface move at different rates. This phenomenon, called differential rotation, sets the Sun apart from rocky planets and even from the giant gas planets that exhibit only modest variations in rotation rate between equator and poles. On the Sun, the difference is substantial. The equatorial regions complete a full rotation in approximately 25 days, while the polar regions take about 35 days. The transition from fast to slow rotation is smooth across latitude, producing a pattern in which adjacent regions of the Sun's surface are continuously shearing past one another. This differential motion is not a surface curiosity. It penetrates deep into the solar interior and drives some of the most important processes in solar physics. Understanding why the Sun rotates differentially requires looking at the interplay between convection, rotation, and magnetic fields in the solar interior. The outer third of the Sun, by radius, is called the convection zone, a region in which energy is transported outward by the bulk motion of hot gas. Convection cells form in this region, with hot plasma rising from below, cooling at the surface and sinking back down. These motions are not random. They are organized by the Sun's rotation, with the result that the convection cells transport not only heat, but also angular momentum. The detailed dynamics produce the observed pattern in which equatorial regions accelerate at the expense of polar regions. This is the opposite of what would happen on a rotating sphere with no internal flows, where conservation of angular momentum would tend to produce faster rotation at the poles. The differential pattern on the Sun is a clear sign that internal dynamics are actively shaping the rotation. Below the convection zone lies the radiative zone, where energy is transported by photons rather than by bulk motion. This region rotates as a solid body, with all parts moving at approximately the same rate. The transition between the differentially rotating convection zone and the uniformly rotating radiative zone occurs in a thin layer called the tachocline, discovered through detailed observations of solar oscillations in the late 20th century. The tachocline is a region of strong shear, where the differential rotation above meets the uniform rotation below. This shear is thought to play a critical role in the generation of the Sun's magnetic field, because stretching and twisting of magnetic field lines in a shearing flow can amplify magnetic energy enormously. The Sun's magnetic field is one of the most important consequences of its rotation. The field is generated by a process called the solar dynamo, in which the motion of conductive plasma in the presence of an initial magnetic field produces electric currents that in turn create more magnetic field. The differential rotation stretches the magnetic field lines, while the convective motions twist them into complex patterns. The cycle of amplification and reconfiguration produces the familiar 11-year solar cycle, during which the Sun goes through periods of maximum and minimum activity. At solar maximum, the surface is covered with sunspots and active regions, while at solar minimum, these features largely disappear. Every 11 years, the polarity of the magnetic field reverses, so the complete magnetic cycle is actually 22 years long. The connection between rotation and magnetism on the Sun has practical consequences. Solar activity drives space weather, the variable conditions in interplanetary space that affect satellites, communications, power grids, and astronauts. Solar flares, sudden releases of magnetic energy on the Sun's surface, can send bursts of high-energy radiation and charged particles toward Earth. Coronal mass ejections, large eruptions of plasma into space, can produce geomagnetic storms when they encounter the Earth's magnetic field. All of these phenomena trace their ultimate origin to the interplay between rotation and magnetic field generation in the solar interior. Without differential rotation, the solar dynamo would operate differently, and the magnetic activity of the Sun might be much reduced. The rotation rate of the Sun has not been constant throughout its history. Like all stars, the Sun was born from a collapsing cloud of gas, and the conservation of angular momentum during that collapse left the young Sun rotating much faster than it does today. Observations of young Sun-like stars in nearby star-forming regions show that they often rotate with periods of a few days, far faster than the Sun's current 25-day rotation period at the equator. Some young stars rotate so rapidly that they are noticeably flattened by centrifugal effects. Over the course of stellar evolution, these rapidly rotating young stars slow down through a process called magnetic braking. Magnetic braking works through the interaction between a star's magnetic field and the stellar wind, the continuous outflow of charged particles from the stellar surface. As the wind flows outward, it carries with it the magnetic field lines anchored in the star. Because the wind is forced to corrotate with the star out to a considerable distance, the angular momentum carried by the wind is much larger per particle than it would be without the magnetic coupling. Over hundreds of millions of years, this magnetized wind carries away substantial angular momentum, slowing the star's rotation. The Sun has been losing angular momentum through this process throughout its life, and continues to do so today. The current rotation rate is much slower than it was when the Sun was a young star, and it will continue to decrease, although the rate of slowing is now relatively gradual. The braking mechanism is so effective that the rotation rates of stars can be used to estimate their ages in a technique called gyrochronology. Younger stars rotate faster, older stars rotate slower, and the relationship is regular enough that measuring a star's rotation period provides a rough estimate of how long it has been on the main sequence. This technique has been particularly valuable for studying populations of stars in clusters, where ages can be cross-checked through other methods. The systematic slowing of stellar rotation with age is a clear illustration of how angular momentum, conserved at the most fundamental level, can be transferred away from a star and out into the surrounding space. The internal structure of the Sun also exhibits subtleties that go beyond the simple convection zone and radiative zone picture. Detailed measurements using helioseismology, the study of acoustic waves propagating through the Sun's interior, have revealed flow patterns called meridional circulation. This is a slow flow of plasma from the equator toward the poles at the surface, and a return flow from the poles back to the equator at deeper levels. The meridional circulation is much weaker than the rotational motions, but it plays an important role in transporting magnetic fields and other quantities across the Sun. The complete picture of solar rotation involves the differential rotation, the meridional circulation, and various smaller-scale flows, all interacting in complex ways within the convection zone. Other stars exhibit their own variations on these themes. Stars more massive than the Sun tend to rotate faster, both because they were born from clouds with different angular momentum properties and because their magnetic braking is less effective. Some massive stars rotate so rapidly that they are significantly flattened, with equatorial radii noticeably larger than polar radii. The fastest rotating stars known approach the critical rotation rate at which centrifugal effects at the equator would equal the gravitational pull, threatening to fling material off into space. Some stars observed near this limit are actively losing mass in equatorial disks that surround them. The behavior of stellar rotation across the full range of stellar types reveals a rich diversity of dynamical states, all governed by the same underlying principles of angular momentum conservation and stellar evolution. Stars at the ends of their lives undergo dramatic changes in rotation as well. When a massive star explodes as a supernova, the core collapses to form a neutron star or black hole, and the conservation of angular momentum causes the resulting compact object to spin extremely rapidly. Neutron stars with radii of only about 10 kilometers can rotate hundreds of times per second. The fastest known examples, called millisecond pulsars, complete a full rotation in just a few thousandths of a second. The enormous rotational kinetic energy of these objects represents the concentrated angular momentum of the original massive star, dramatically amplified by the collapse. Observations of these extreme rotators provide some of the most precise tests of physics under conditions impossible to reproduce in any laboratory. The Sun, in this broader context, is a middle-aged star of moderate mass, rotating at a modest rate after billions of years of magnetic braking. It is neither among the fastest nor the slowest rotators in its category, and its rotation rate will continue to decrease gradually as it continues to lose angular momentum through its wind. The features we observe on the Sun today, including the 11-year activity cycle and the magnetic field that shapes space weather across the solar system, are direct consequences of the rotational state in which the Sun currently finds itself. A different rotation rate would produce a different magnetic environment, and a different magnetic environment would produce different effects on the planets. The conditions for life on Earth, in this sense, are intimately tied to the particular rotational state of the parent star, just as they are tied to the rotational state of the planet itself. But while the Sun's rotation follows a relatively orderly pattern, the same cannot be said of every planet in the system. The motions of the worlds that orbit the Sun reveal a more complex story, one that includes notable exceptions to the otherwise consistent pattern of rotation. The planets of the solar system share a striking general pattern. They orbit the Sun in nearly the same plane, they orbit in the same direction, and most of them rotate on their axes in that same direction as well. This consistency is not accidental. It is a direct legacy of the original protoplanetary disk from which all the planets formed. The disk was rotating in a particular direction, inherited from the parent molecular cloud, and the bodies that emerged from it carried that rotation forward as both orbital motion and axial spin. The alignment of orbits, the direction of rotation, and even the rough orientation of the planetary axes all preserve information about the structure of that ancient disk. Yet the pattern is not perfect. Several planets deviate from the expected behavior in ways that have required astronomers to construct careful explanations involving specific events in solar system history. Two cases stand out as particularly puzzling. Venus rotates extremely slowly and in the opposite direction from most other planets. Uranus rotates on its side, with its axis tilted by 98 degrees from the perpendicular to its orbital plane. These anomalies are not minor variations on the standard story. They are radical departures that demand specific explanation. Understanding them illuminates not only the histories of those particular worlds, but also the broader question of how rotational states evolve over the lifetime of a planetary system. Begin with Venus. The planet completes a single rotation on its axis in about 243 Earth days, which is actually longer than its orbital period around the Sun of about 225 Earth days. This means that a day on Venus, measured from one sunrise to the next, is shorter than its rotational period because the planet's orbital motion partially compensates for its slow spin. The retrograde direction of rotation, opposite to that of most other planets, is even more striking. From the perspective of an observer above the North Pole of the solar system, the planets generally rotate counterclockwise, but Venus rotates clockwise. The Sun rises in the west and sets in the east, the reverse of what occurs on Earth. Several explanations have been proposed for this unusual configuration, and they probably involve a combination of factors. One leading explanation involves the thick atmosphere of Venus. The planet is enveloped by a dense atmosphere of carbon dioxide that extends to great heights above the surface. The atmospheric mass is so substantial that thermal tides, driven by the heating of the day side and cooling of the night side, can exert torques on the solid body of the planet. Combined with gravitational tides raised by the Sun, these atmospheric tides may have braked an originally faster rotation over geological time, eventually reversing the direction of rotation entirely. Numerical simulations show that such a scenario is plausible, given the particular conditions on Venus, including its proximity to the Sun, its thick atmosphere, and the absence of a large moon to stabilize its rotation. An alternative explanation invokes a massive impact in the early history of the planet, an event that struck Venus in such a way as to reverse its rotation directly. The truth may involve both mechanisms, with an early impact disturbing the rotation and atmospheric tides completing the transition over the following billions of years. The case of Uranus is even more dramatic. The planet is tilted on its side, with its rotational axis lying nearly in the plane of its orbit. As a result, the poles of Uranus alternately face the Sun during its 84-year orbit, producing extreme seasonal patterns unlike those of any other major planet. Each pole experiences 42 years of continuous sunlight, followed by 42 years of continuous darkness. The standard explanation for this extreme tilt involves a major collision early in the planet's history. A large body, perhaps as massive as the Earth, is thought to have struck Uranus before the solar system had fully settled into its present configuration, knocking the planet over and producing the rotational state we observe today. The system of Uranian moons orbits in the equatorial plane of the planet, consistent with the moons having formed from material left over after the impact or having reorganized themselves around the modified rotation axis. These anomalies illustrate an important principle. The general pattern of planetary rotation reflects the orderly conditions of the protoplanetary disk, but the particular state of any given planet depends on the specific events in its history. Collisions, tidal interactions, gravitational perturbations, and atmospheric effects can all alter rotation over time. The protoplanetary disk provides the initial conditions, but billions of years of subsequent dynamics shape the final configurations. The result is a solar system with broad statistical regularities, but also individual peculiarities that require detailed investigation to understand. Even among planets that follow the general pattern, there is substantial variation. The rotation periods range from about 10 hours for Jupiter, the fastest rotating of the major planets, to over 200 days for Venus, the slowest. The axial tilts range from near zero for Mercury and Jupiter to roughly 26 degrees for Saturn, with Earth and Mars falling in between. These variations reflect different formation histories, different masses, different compositions, and different interactions with neighboring bodies. Each planet is a unique case, even within the general framework of how solar systems form and evolve. The giant planets are particularly interesting because their rapid rotation produces visible flattening. Jupiter, despite being much larger than Earth, completes a rotation in less than 10 hours. The centrifugal effect of this rapid spin distorts the planet noticeably, with the equatorial diameter being about 7% larger than the polar diameter. The flattening can be seen in any decent telescopic image of Jupiter. Saturn rotates only slightly more slowly but is less massive and has a lower density, so its flattening is even more pronounced. The polar regions of Saturn are visibly closer to the planet's center than the equatorial regions, producing an ablateness that is striking even in casual observation. The internal structure of these planets contributes to their rotation behavior, with deep atmospheric layers and possibly different rotation rates at different depths. The atmospheres of the giant planets exhibit their own rotational features. Jupiter and Saturn both display banded structures, alternating dark and light bands that run parallel to the equator. These bands represent regions of differential atmospheric rotation, with adjacent bands moving at slightly different speeds. Where bands meet, complex turbulent features develop, including the famous Great Red Spot on Jupiter, an enormous storm that has persisted for centuries. The detailed dynamics of these atmospheres depend on the rotation of the planet, the temperature differences between equator and poles, and the internal heat sources of the planets themselves. Jupiter and Saturn both emit more energy than they receive from the Sun, indicating ongoing internal processes that supply additional heat. Combined with rotation, this internal heating drives circulation patterns that produce the striking visible features. The smaller worlds of the solar system, including the dwarf planets and the major moons, also exhibit a range of rotational behaviors. Pluto and its largest moon, Charon, are mutually tidally locked, always showing the same faces to each other. This is a relatively unusual configuration in which both bodies are locked rather than just the smaller one. Triton, the largest moon of Neptune, orbits in the retrograde direction, opposite to the rotation of its parent planet. This unusual orbit suggests that Triton was not formed in place, but was captured by Neptune from elsewhere in the outer solar system, possibly originally being a Kuiper belt object similar to Pluto. The capture would have required a complex dynamical history, perhaps involving the disruption of an original binary partner. The detailed measurements of planetary rotations have also been used to probe the interiors of the planets. The rate at which a planet rotates, combined with its mass and shape, constrains its internal density distribution. Slight wobbles in the rotation axis, called precession and nutation, depend on the internal structure of the planet. Spacecraft missions to the outer planets have refined our understanding of the masses and rotational characteristics of these worlds, providing information about their interiors that would otherwise be inaccessible. The rotations of the planets are not just decorative features, they are diagnostic tools that scientists use to understand the formation and structure of bodies that may never be directly observed in detail. The variety of planetary rotations in our solar system also informs the study of planets around other stars. With over 5,000 confirmed exoplanets now identified, astronomers can ask whether the patterns seen here are common or unusual. The challenge is that measuring the rotation of exoplanets is much harder than measuring their orbital periods. Still, some progress has been made. A few exoplanets have had their rotation rates estimated from spectroscopic measurements of the Doppler broadening of their light, and others have been studied through the timing of transits across their parent stars. The data so far suggest that planetary rotations vary widely in other systems, just as they do in our own. The general principles of formation produce broad regularities, but the specific outcomes depend on the histories of individual systems. The picture that emerges from all this is that planetary rotation is the product of many influences operating across vast timescales. The initial spin inherited from the protoplanetary disk provides the starting point, but subsequent events shape the final configuration. Collisions, tidal interactions, atmospheric effects, and gravitational perturbations all contribute to the specific rotational state of any given planet. The remarkable thing is not that planets exhibit some variability in their rotations, but that the underlying regularities are as strong as they are. The pattern of generally aligned, generally prograde rotation across most planets is itself evidence of the orderly conditions in which they formed. The exceptions, dramatic as they are exceptions to a real pattern, not signs that no pattern exists. And the same dynamics that shape major worlds also operate on the much smaller bodies that drift between them, producing rotational behaviors that vary in intriguing ways from one tiny object to another. The asteroids and other small bodies of the solar system are too modest in size to be shaped significantly by their own gravity. They retain irregular forms, sometimes resembling potatoes, peanuts, or fragmented rocks rather than the smooth spheres that dominate the larger members of the planetary system. Their rotational behaviors are correspondingly varied, reflecting the chaotic histories of objects that have been shaped by countless collisions, fragmentations, and gravitational encounters over billions of years. Studying these small bodies provides a window into processes that operate on all rotating objects, but are usually masked in larger bodies by the effects of gravity and internal dynamics. On asteroids, the underlying physics is exposed and accessible to direct observation. The rotation rates of asteroids span an enormous range. The smallest asteroids, those less than about 150 meters across, sometimes spin extraordinarily rapidly, completing a rotation in just a few minutes. The fastest rotators of this size class would fly apart if they were not held together by some force beyond their own weak gravity. The cohesive forces in such bodies are thought to involve van der Waals interactions between dust grains or other forms of structural rigidity, indicating that some of these objects are essentially solid pieces of rock rather than the rubble piles that constitute many larger asteroids. The boundary between these two classes is itself revealing. Above a certain size, no asteroids are observed rotating faster than a critical rate of about 2 hours per rotation. This barrier, called the rotational disruption limit, suggests that larger asteroids are typically loose collections of fragments rather than solid bodies, with gravitational binding too weak to hold them together against the centrifugal effects of rapid rotation. The shapes of asteroids influence their rotational dynamics in ways that have no counterpart among major planets. A truly spherical body rotates around any axis with equal stability. An elongated body, by contrast, rotates most stably around its shortest axis, the one that gives the lowest moment of inertia for the given mass distribution. If an asteroid begins to tumble around any other axis, internal dissipation will eventually bring it back to rotation around the shortest axis, although this process can take a long time for rigid bodies. Some asteroids are observed to be in non-principal axis rotation, tumbling in complex ways that cannot be described by a single rotation axis. These tumblers have been disturbed from their stable configurations relatively recently in cosmic terms, often by collisions or by gravitational encounters with larger bodies. Collisions are a major influence on asteroid rotation. In the main asteroid belt between Mars and Jupiter, collisions between asteroids have been occurring continuously throughout the history of the solar system. Each collision transfers angular momentum, can change the rotation rate, can alter the direction of the rotation axis, and can even destroy the bodies involved entirely. The smaller fragments produced by such collisions carry their own rotational signatures, often quite different from those of their parent bodies. Over billions of years, the cumulative effect of countless collisions has produced the diverse population of rotation states observed today. Some asteroids rotate quickly because recent collisions imparted angular momentum to them. Others rotate slowly because their angular momentum was lost in past collisions. The statistics of asteroid rotation rates carry information about the collisional history of the asteroid belt. A subtler influence on asteroid rotation comes from the interaction between the asteroid and sunlight. Sunlight carries momentum, and when it strikes a body, some of that momentum is transferred. For most large objects, this radiation pressure effect is too small to matter. But for small bodies, especially those with irregular shapes, the cumulative effect over millions of years can be significant. The Yarkovsky effect, named after the Russian engineer who first proposed it in 1900, describes how the daytime surface of an asteroid, heated by the sun, re-radiates that heat in the infrared after the surface has rotated to the night side. The asymmetry between the absorbed sunlight and the re-radiated heat produces a small thrust that can alter the orbit of the asteroid over time. A related effect called the Yorp effect, after the initials of the four scientists who developed the theory, describes how this same asymmetric radiation can alter the rotation state of the asteroid. The Yorp effect can either spin up or spin down an asteroid, depending on its shape and orientation. It can also change the direction of the rotation axis. For small asteroids with sufficient time, the Yorp effect can produce dramatic changes in rotation. The fastest rotating small asteroids may have been spun up to their current rates by Yorpy acceleration acting over millions of years. The slowest rotators may have been similarly slowed by the same mechanism operating in the opposite direction. Direct observation has confirmed the Yorp effect in several cases. The asteroid known as 1998 KW4, for example, is a binary system in which a rapidly rotating primary asteroid has a smaller companion in close orbit. The primary asteroid is so close to the rotational disruption limit that material has apparently been flung off from its equator and accumulated into the secondary body. This configuration is now thought to be common among small near-Earth asteroids, with Yorp-driven spin-up producing binary systems through equatorial mass shedding. The orbit and rotation rate of the smaller companion provide further evidence of the dynamical history, and the entire system serves as a natural laboratory for studying how radiation forces shape small bodies over long times. The comets, although composed of different materials than asteroids, exhibit similar variability in their rotations. Comets are primarily composed of ices and dust, and as they approach the sun, the heated surface ices sublimate, producing jets of gas and dust that drive the formation of comet tails. The jets, however, do not emerge uniformly from the comet nucleus. They emerge from specific active regions on the surface, and the resulting torques can change the rotation of the nucleus. Some comets have been observed to alter their rotation rates significantly between successive approaches to the sun, providing direct evidence of how outgassing affects rotational dynamics. The rotation rates of comet nuclei tend to be slower than those of similar-sized asteroids, partly because comets are typically larger and partly because their outgassing activity acts as a brake. The objects of the Kuiper belt, beyond the orbit of Neptune, also exhibit a range of rotational behaviors. These bodies are typically composed of ices and rocky material, similar to comet nuclei, but mostly never having been heated enough to outgas significantly. Their rotations have been studied through light curve observations, which detect the periodic variations in brightness produced as irregularly shaped or marked bodies rotate. The data show that Kuiper belt objects span a range of rotation rates similar to that of asteroids, with some elongated objects exhibiting double-peaked light curves indicating significant non-spherical shapes. The dwarf planet Haumea, in particular, is famous for its extreme elongation, with a rotation period of less than 4 hours and a shape that has been distorted into a triaxial ellipsoid by its rapid spin. Haumea may also be at the boundary of rotational stability, with its rapid rotation potentially related to a past collision that gave it both its current rotation and its small system of moons. The tiny moons of the major planets provide yet another window into rotational dynamics. The two moons of Mars, Phobos and Deimos, are both small irregular bodies, almost certainly captured asteroids based on their compositions and shapes. Both are tidally locked to Mars, although their orbits and rotational states have evolved over time. Phobos is gradually spiraling inward toward Mars and will eventually either break apart due to tidal forces or impact the planet, in either case within about 50 million years. The smaller moons of the giant planets, of which dozens have been discovered, include many irregular and unusual rotators. Hyperion, a moon of Saturn, is particularly notable for being in chaotic rotation. Its rotation rate and axis change unpredictably, producing a tumbling motion that cannot be described by any single fixed rotation period. The chaos arises from the combination of Hyperion's elongated shape, its eccentric orbit, and its gravitational interactions with the nearby major moon Titan. The chaotic rotation of Hyperion is a striking example of a phenomenon that probably occurs more widely in nature, but is hard to detect for bodies that have already settled into stable configurations. Chaos can emerge in rotational dynamics when small influences become amplified through nonlinear interactions, producing behavior that is fundamentally unpredictable beyond short timescales. The recognition of chaotic rotation in Hyperion has prompted searches for similar behavior in other small bodies, with some candidates identified. The general lesson is that rotational dynamics, even in the absence of dramatic events, can be more complex than the simple steady rotation observed for most large planets. Small bodies with their irregular shapes and weaker self-gravity reveal the underlying complexity that is masked in the major worlds. Even among the apparently steady rotators, careful study reveals subtle variations. The asteroids that have been visited by spacecraft, including Eros, Itokawa, Bennu, Ryugu, and others, have all been found to have complex surface features and rotational histories that are reflected in the distributions of boulders, craters, and dust on their surfaces. The asteroid Bennu, in particular, was visited by the OSIRIS-REx spacecraft, which spent nearly 2 years orbiting and studying the body before collecting a sample and returning it to Earth. The mission revealed that Bennu is a rubble pile, loosely held together by gravity, and that its rotation is gradually accelerating due to the Yorpi effect. Active material on its surface, including the periodic ejection of small particles from specific regions, suggests that the rotation is connected to surface dynamics in ways that were not previously appreciated. The picture that emerges from the study of small body rotation is one of remarkable diversity, shaped by processes operating across an enormous range of timescales and intensities. Some asteroids and comets have rotational histories dominated by single major events, such as collisions or close encounters. Others have been shaped primarily by the slow accumulated effects of countless small influences, including radiation forces and minor perturbations. The result is a population of bodies that, taken together, document the dynamical history of the solar system. Each asteroid, each comet, and each small moon carries information about the conditions and events that shaped it. Their rotations are not just curiosities. They are records, encoded in motion, of the processes that have produced the solar system as we observe it today. And yet, dramatic as the rotations of these small bodies can be, they pale beside the rotations of objects whose gravity is so intense that not even light can escape. Black holes are objects of such extreme density that their gravitational pull prevents anything, including light, from escaping once it crosses a particular boundary called the event horizon. Despite this defining property, black holes are not featureless or inert. They carry properties inherited from the matter that formed them, including mass, electric charge, and angular momentum. The angular momentum of a black hole, often described as its spin, has consequences that extend far beyond the event horizon itself, distorting the structure of spacetime in ways that can be measured and even, in some cases, exploited as a source of energy. The study of rotating black holes has become one of the most active areas in modern theoretical and observational astrophysics, revealing phenomena that test the limits of our understanding of gravity. The mathematical description of a rotating black hole was developed by the New Zealand mathematician Roy Kerr in 1963. Kerr produced a solution to Einstein's equations of general relativity that described the geometry of spacetime around a rotating massive body. This Kerr solution remains the standard mathematical framework for understanding rotating black holes, and it has properties that distinguish it sharply from the simpler case of non-rotating black holes described by the Schwarzschild solution. A rotating black hole has not one but two characteristic surfaces. The event horizon, the boundary beyond which nothing can escape, is the inner of these. Outside it lies a larger region called the ergosphere, where the rotation of the black hole drags spacetime itself in such a way that no observer can remain stationary relative to the distant stars. This dragging of spacetime by a rotating massive object is called frame dragging, and it is one of the most counterintuitive predictions of general relativity. In the vicinity of a rotating body, the very fabric of spacetime is twisted in the direction of rotation. Any object near a rotating black hole, no matter how powerful its engines or how rigid its construction, cannot resist being carried along with the rotating spacetime. Inside the ergosphere, this dragging is so severe that maintaining stationary position relative to distant reference points is impossible. The frame dragging effect is not unique to black holes. It occurs around any rotating massive object, including the Earth, but the effect is so weak around ordinary bodies that detecting it required extremely sensitive experiments. The Gravity Probe B mission, launched in 2004, measured frame dragging by the Earth using highly sensitive gyroscopes in orbit, confirming the prediction of general relativity to high precision. Around a rotating black hole, frame dragging dominates the dynamics in striking ways. Inside the ergosphere, any object must rotate with the black hole, regardless of its initial state of motion. The boundary of the ergosphere is not the event horizon itself, but lies outside it, except at the poles where the two surfaces touch. The region between the event horizon and the outer boundary of the ergosphere is therefore accessible to outside observers. Anything that enters this region can still potentially leave, although it must rotate with the black hole while it is inside. This accessibility leads to a remarkable possibility, first identified by the physicist Roger Penrose. An object entering the ergosphere can split into two pieces, with one piece falling into the black hole and the other escaping to infinity with more energy than the original object possessed. The additional energy comes from the rotational energy of the black hole itself, which decreases in the process. This Penrose mechanism is theoretical, but it illustrates a deeper truth about rotating black holes. They possess enormous reserves of rotational energy that, in principle, can be extracted by external processes. For a maximally rotating black hole, the rotational energy can be as much as 29% of the total mass energy of the black hole, an astonishing fraction. While the Penrose mechanism itself is difficult to realize in practice, related phenomena involving magnetic fields can extract rotational energy from black holes much more efficiently. The Blandford-Znajek mechanism, proposed in the 1970s, describes how magnetic field lines threading a rotating black hole can transfer rotational energy to surrounding plasma, producing the powerful jets observed emanating from many active galactic nuclei. This mechanism is believed to power some of the most energetic phenomena in the universe, including the relativistic jets that extend across millions of light years from the centers of certain galaxies. The rotation of supermassive black holes at the centers of galaxies has been measured through various techniques, with the spin parameters of many such objects now estimated with reasonable confidence. The supermassive black hole at the center of our own galaxy, Sagittarius A star, has been studied through the motions of nearby stars and through the imaging of its surrounding plasma by the Event Horizon Telescope. The first ever image of a black hole, released in 2019, showed the supermassive black hole at the center of the galaxy Messier 87, surrounded by a ring of glowing plasma. The asymmetry of this ring, with one side brighter than the other, provided evidence for the rotation of the black hole, since the Doppler effect enhances the brightness of plasma moving toward the observer and dims that moving away. Subsequent observations have refined these measurements and produced similar images of Sagittarius A star, also revealing rotational signatures. The rotation of stellar mass black holes, those produced by the collapse of massive stars, has been measured through observations of X-ray emission from material accreting onto them. As material falls toward a black hole, it accumulates in an accretion disk that radiates intensely at X-ray wavelengths. The innermost edge of this disk is bounded by the innermost stable circular orbit, beyond which material plunges directly into the black hole. The radius of this innermost stable circular orbit depends on the rotation of the black hole. A more rapidly rotating black hole drags spacetime more strongly, allowing stable orbits closer to the event horizon. By measuring the X-ray spectrum from material near the innermost stable circular orbit, astronomers can estimate the rotation of the black hole. The results show that stellar mass black holes span a wide range of rotation rates, from nearly zero to nearly the maximum allowed by general relativity. The maximum possible rotation of a black hole is a fascinating feature of the Kerr solution. As the spin parameter approaches its maximum value, the event horizon shrinks toward the inner Cauchy horizon, and the spacetime structure becomes increasingly complex. In the limit of maximal rotation, the two horizons merge and the black hole becomes what is called an extremal Kerr black hole. Pushing the rotation beyond this limit is not possible within the framework of general relativity, because doing so would expose the central singularity to outside observers, violating the cosmic censorship conjecture proposed by Roger Penrose. While the conjecture remains unproven, all known physical mechanisms for adding angular momentum to a black hole, including accretion of rotating material and mergers with other black holes, are believed to respect the maximum spin limit. Black hole mergers have provided some of the most direct evidence about black hole spins. When two black holes orbit each other and eventually merge, they emit gravitational waves that carry detailed information about the masses, spins, and orientations of the original black holes. The Laser Interferometer. Gravitational Wave Observatory, or LIGO, and its European counterpart Virgo, have detected numerous black hole mergers since the first observation in 2015. The waveforms of these events have been analyzed to extract information about the spins of the merging objects. The results show that black holes formed from stellar collapse can have a range of spins, with some apparently slowly rotating and others spinning rapidly. The reason for this diversity is still under investigation, but it likely involves the conditions in the stellar progenitors and the dynamics of any binary system in which the black holes formed. The product of a black hole merger is itself a rotating black hole, with a spin determined by the masses and spins of the original components and by the orbital angular momentum at the moment of merger. In general, the resulting black hole has a spin that approaches but does not reach the maximum value. The final spin depends in complex ways on the geometry of the merger, with mergers between black holes of similar mass tending to produce final black holes with substantial spin. These final spins are consistent with theoretical predictions from numerical simulations of merging black holes, providing yet another confirmation of the predictions of general relativity in the strong field regime. The connection between black hole rotation and the production of jets is particularly significant. Many of the most luminous objects in the universe, including quasars and active galactic nuclei, are powered by accretion under rotating supermassive black holes. The rotational energy of these black holes provides a vast reservoir of energy that can be extracted through electromagnetic interactions with surrounding plasma. The resulting jets, often relativistic and extending across enormous distances, are among the most prominent features in radio surveys of the sky. Galaxies hosting active nuclei can outshine their normal stellar populations by orders of magnitude, with much of this luminosity ultimately derived from the rotation of the central black hole. Some of the most extreme phenomena in astrophysics involve the rotation of newly formed black holes. Gamma-ray bursts, brief but extremely intense flashes of gamma rays detected from across the universe, are thought to be produced when massive stars collapse to form rapidly rotating black holes, with the rotation playing a crucial role in launching the relativistic jets that produce the observed emission. The connection between rotation and energy release in these events is striking, with the rotational energy of the newly formed black hole providing the power that drives some of the most luminous events ever recorded. Without rotation, these phenomena would not exist, and many of the brightest signals in the universe would simply not be produced. The study of black hole rotation has thus opened a remarkable window into the physics of gravity in its most extreme manifestation. From the dragging of space-time to the extraction of energy through magnetic processes, from the production of cosmic jets to the spectacular mergers detected by gravitational wave observatories, the rotation of black holes is woven into many of the most dramatic phenomena observed in modern astrophysics. The mathematical framework of the Kerr solution, developed in the early 1960s, continues to provide the foundation for understanding these phenomena, and its predictions have been verified across a remarkable range of conditions. Yet the questions that remain are equally compelling. What determines the spin distribution of newly formed black holes? How do supermassive black holes acquire their rotation across cosmic history? And what is the role of black hole rotation in shaping the galaxies that host them? These questions connect the rotation of compact objects to the larger structures of which they are part, drawing attention to the rotational dynamics of galaxies themselves. Galaxies rotate, and their rotation reveals one of the most profound puzzles in modern astronomy. To the casual observer, a spiral galaxy appears as a beautiful pattern of stars and gas arranged into graceful arms that curve outward from a central bulge. But when astronomers measure the actual motions of stars and gas within such a galaxy, they discover something deeply unexpected. The outer regions move at speeds that cannot be explained by the gravitational pull of the visible matter alone. This discrepancy, first noticed in detail by the American astronomer Vera Rubin in the 1970s, has become one of the strongest pieces of evidence for the existence of dark matter, an invisible substance that appears to dominate the gravitational structure of galaxies and that has resisted all attempts at direct detection. The rotation of galaxies, however, begins as a much more straightforward phenomenon. Like any large gravitating system, a galaxy that forms from the collapse of a rotating gas cloud will inherit substantial angular momentum. The collapsing material, organized by gravity and structured by rotation, settles into a flattened disk in which most of the stars and gas reside. The central bulge represents material that fell more directly toward the center without forming organized circular motion. The disk itself, however, is a structure dominated by rotation, with stars and gas following roughly circular orbits around the galactic center. This basic picture, while incomplete, captures the essential geometry of spiral galaxies and explains many of their observed features, including the alignment of stars in the disk plane and the existence of distinct populations with different orbital characteristics. The Milky Way, our own galaxy, exemplifies this structure. The Sun orbits the galactic center at a distance of about 26,000 light-years, moving at a speed of approximately 220 kilometers per second. A complete orbit takes roughly 230 million years, a span of time so long that the Sun has completed only about 20 galactic orbits since its formation 4.5 billion years ago. The galaxy as a whole rotates differentially, with stars at different distances from the center completing their orbits in different times. This differential rotation gradually winds up any feature that exists in the galactic disk, producing the spiral patterns visible in many galaxies. The spiral arms themselves are not solid structures. but rather density waves that propagate through the galactic disk, compressing gas and triggering the formation of new stars as they pass through. The pattern of stellar motions in a rotating galaxy follows certain expected rules if we assume that the gravity is provided entirely by the visible matter. Near the center, where the mass is concentrated, the rotation should be approximately like that of a solid body, with speed increasing roughly linearly with distance. Beyond the densest central regions, the rotation should decrease with distance, following a Keplerian pattern in which orbital speed declines as the inverse square root of distance from the center. This is exactly how the planets behave in the solar system, where the mass is overwhelmingly concentrated in the Sun, and outer planets move more slowly than inner ones. A galaxy whose mass distribution traced the distribution of visible matter would show a similar Keplerian decline in rotation speed at large distances. This is not what astronomers observe. When the rotation curves of galaxies are measured, plotting orbital speed against distance from the galactic center, the curves do not decline in the expected Keplerian way. Instead, they typically remain roughly flat out to the largest distances at which orbital motion can be measured. Stars and gas at the outer edges of galaxies move at speeds comparable to those of material in the inner regions, despite being far from most of the visible mass. The implication is unavoidable. There must be substantial additional mass that is not visible, distributed in a way that produces the observed rotation curve. Vera Rubin and her colleague Kent Ford developed the observational techniques that establish this discrepancy across many galaxies. By measuring the Doppler shifts of light from different regions of a galaxy, they could determine the orbital speeds of material at various distances from the galactic center. Their measurements, published in the 1970s and refined over subsequent decades, showed flat rotation curves to be a nearly universal feature of spiral galaxies. The visible matter could not explain these patterns. Something else, something invisible, must be providing the additional gravitational pull required to keep the outer regions of galaxies in their observed orbits. The proposal that emerged from these observations, although it had been suggested earlier in different contexts, was that galaxies are embedded in extended halos of dark matter. This dark matter does not emit, absorb, or reflect light to any detectable degree. It interacts gravitationally with ordinary matter, but otherwise barely interacts at all, making it invisible to telescopes operating at any wavelength. The dark matter is thought to extend far beyond the visible disk of a galaxy, forming a roughly spherical halo that dominates the gravitational mass of the system. Within this halo, the visible galaxy is a relatively small structure, like the bright tip of a much larger, mostly invisible iceberg. The total mass of the dark matter in a typical spiral galaxy may exceed the mass of all visible matter by a factor of 5 to 10. The evidence for dark matter does not rest on rotation curves alone. Multiple independent lines of evidence point to the same conclusion. Gravitational lensing, the bending of light by mass, allows astronomers to map the distribution of matter in clusters of galaxies, and these maps consistently show much more mass than can be accounted for by visible objects. The observed motions of galaxies within clusters require similar amounts of unseen mass to hold the clusters together against the disruptive effects of their internal motions. The patterns of fluctuations in the cosmic microwave background radiation, the relic light from the early universe, are also consistent with the presence of a substantial amount of cold dark matter influencing the gravitational evolution of structure. The combined weight of these arguments has made the existence of dark matter a standard component of the modern cosmological picture, even though no direct detection of dark matter particles has yet been achieved. The dark matter halos play a critical role in galactic rotation. As a galaxy forms, gas falls into the gravitational potential well of a pre-existing dark matter halo, cooling and settling into a disk through the loss of energy by radiation. The angular momentum of the infalling gas is preserved, but the energy decreases, with the result that the gas ends up in circular orbits at radii determined by the balance between angular momentum and gravitational potential. The rotation of the resulting galactic disk reflects both the distribution of visible matter and the larger distribution of dark matter that surrounds it. Without the dark matter halo, the disk would have a different rotation curve and might not even be stable against various disruptive processes that operate on long timescales. The rotation of galaxies also tells us something about how galaxies have evolved over cosmic time. The angular momentum that galaxies possess today must have been acquired during their formation. The leading theoretical picture involves tidal interactions between protogalactic regions in the early universe. As dense regions began to collapse to form the first galaxies, the gravitational tug of neighboring overdensities exerted torques that imparted angular momentum to the contracting material. This process, known as tidal torque theory, predicts that galaxies should have angular momenta related to the patterns of structure in the early universe. The detailed predictions can be tested against observations, and the agreement is generally good, suggesting that the basic picture of how galaxies acquired their spin is correct. The morphology of galaxies, the distinction between spiral galaxies and elliptical galaxies, is also tied to their rotation. Spiral galaxies, with their organized disks and ongoing star formation, are dominated by rotational motion. Elliptical galaxies, by contrast, are largely supported against gravity by the random motions of their stars rather than by organized rotation. The kinetic energy in an elliptical galaxy is distributed among stars moving in various directions with little net rotation. This distinction is thought to arise from the merger history of the galaxies. Elliptical galaxies are believed to form through major mergers between spiral galaxies, with a violent merging process scrambling the original rotational motions and producing the random patterns observed today. The intermediate morphologies, including lenticular galaxies and various transitional types, fill out the spectrum between purely rotational and purely random support. Modern surveys have revealed even more detail about galactic rotation. Some galaxies, called counter-rotating galaxies, contain populations of stars or gas that rotate in opposite directions. These configurations cannot arise from a single coherent collapse and must instead reflect more complex histories involving the accretion of material from outside or the merging of systems with different initial spins. Other galaxies exhibit warps in their outer disks, with the rotation plane gradually tilting at large radii. The causes of these warps are still debated, but they may involve gravitational interactions with companion galaxies or distortions of the dark matter halo. The variety of rotational behaviors across the population of galaxies provides clues to the diverse histories through which different galaxies have formed and evolved. The largest scales of galactic motion show further patterns. Galaxies cluster together into groups and clusters, and these larger systems exhibit their own rotational tendencies. Galaxy clusters generally have less coherent rotation than individual galaxies, with their dynamics dominated by random motions of member galaxies and by the still larger pull of surrounding structures. Yet, careful measurements have suggested that some clusters do exhibit slight rotation, with the centers and outer regions moving differently in ways that hint at angular momentum on truly enormous scales. The investigation of rotation on these scales is among the most challenging in observational cosmology, requiring measurements of motions across distances so vast that even small rotational effects manifest only as subtle systematic patterns in the data. What emerges from all of this is a picture in which rotation organizes structure across many orders of magnitude in scale, from the orbits of stars within galaxies to the motions of galaxies within clusters. Rotation continues to play a significant role, even as the relative importance of organized rotation versus random motion varies from one scale to another. The rotation curves of galaxies, perhaps more than any other measurement, have driven much of modern cosmology by revealing the dominant role of dark matter in shaping the gravitational structure of the universe. The very fact that we know about dark matter at all owes much to the careful measurement of how galaxies spin, and the continued refinement of these measurements remains central to efforts to understand the dark sector of the cosmos. And as those efforts continue, attention has turned more and more to the precise nature of the dark matter that appears to dominate galactic rotation, prompting investigations into both the particles that might constitute it and the larger structures through which it shapes the cosmos. The recognition that galaxies are embedded in halos of dark matter has shifted the framework for understanding rotation on cosmic scales. The visible galaxy is no longer the principal mass in its own gravitational system. Instead, it is a smaller, brighter component within a much larger and mostly invisible structure that controls the gravitational dynamics. The properties of this dark matter halo, including its mass distribution, its extent, and its detailed shape, determine how stars and gas in the visible galaxy actually move. Untangling these properties has become one of the central tasks of modern astrophysics, with consequences that reach from the smallest dwarf galaxies up to the largest superclusters in the observable universe. The dark matter halo is not simply a passive container for the visible galaxy. It is an actively evolving structure whose history shapes the galaxy within it. According to current theoretical models, dark matter halos form through the gradual collapse and merging of smaller structures in a process called hierarchical assembly. In the early universe, small regions of slightly above average density grew by attracting surrounding material. As these regions reached sufficient density, they collapsed to form bound structures, the first dark matter halos. These small halos then merged with one another to form larger halos, which in turn merged again, building up the hierarchy of structures observed today. Throughout this process, the rotation of each halo evolved through tidal interactions with neighboring structures, ensuring that the largest halos at any epoch tended to have rotational characteristics shaped by their environment. The detailed properties of dark matter halos have been the subject of extensive numerical simulations. These simulations track the motions of large numbers of representative particles under their mutual gravitational attraction, allowing the structure of dark matter halos to be characterized in great detail. The results show that halos typically have a roughly universal density profile, with density decreasing approximately as the inverse of distance from the halo center in the inner regions and falling more steeply at larger distances. This profile, often associated with the work of Julio Navarro, Carlos Frank, and Simon White, has become a standard reference point for comparing observations to theoretical expectations. Halos in these simulations also exhibit characteristic angular momentum distributions. They are typically not strongly rotating in the same sense as the visible galaxies within them. Instead, the angular momentum is distributed throughout the halo in complex ways, with different parts rotating at different rates and even in different directions. The visible galaxy, embedded in this complex structure, manages to organize itself into a coherent rotating disk because the gas component can dissipate energy through radiation, settling into the lowest energy state consistent with its angular momentum. The dark matter, by contrast, cannot easily dissipate energy because it interacts so weakly with itself and with ordinary matter. This difference in dissipation mechanisms explains why the visible galaxy can form a thin rotating disk, while the dark matter halo remains a more extended, less organized structure. The interplay between the visible galaxy and the surrounding dark matter halo affects rotation in subtle ways. The gravitational pull of the dark matter influences the orbits of stars and gas in the visible galaxy. Conversely, the visible galaxy exerts gravitational forces on the dark matter, although these forces are weaker because the visible mass is smaller. Numerical simulations that track both visible and dark matter together produce galaxies whose rotation curves match observations remarkably well, although the details depend on assumptions about the nature of dark matter and the processes by which gas cools and forms stars. The general agreement between simulations and observations has supported the standard cosmological picture, even as some discrepancies at small scales have prompted continued investigation. One persistent puzzle involves the rotation of small dwarf galaxies. These small galaxies should, according to standard simulations, exhibit certain characteristic rotation patterns. In some cases, the observed rotation curves do not match these predictions, with the central regions appearing to rotate more slowly than expected. This discrepancy, sometimes called the core cusp problem, suggests that either the simulations are missing important physics in the central regions of dwarf galaxies, or that the assumptions about dark matter need modification. Possible solutions include more detailed modeling of how supernova explosions and other energetic processes redistribute dark matter in the centers of small galaxies, or modifications to the underlying nature of dark matter itself. The debate continues, with new observations and refined simulations gradually clarifying which factors are most important. The detection of dark matter through means other than rotation curves has remained elusive. Despite decades of effort, no experiment has produced a confirmed direct detection of dark matter particles. The leading candidates have included weakly interacting massive particles, or WIMPs, hypothetical particles predicted by various extensions of the standard model of particle physics. Large underground detectors, shielded from cosmic ray backgrounds, have searched for the occasional interaction of dark matter particles with ordinary atoms. So far, these experiments have yielded only upper limits on the interaction rates, ruling out parts of the theoretical parameter space, but leaving room for many possibilities. Alternative candidates, including axions and other light particles, are being searched for through different experimental approaches. The current situation is that we have strong gravitational evidence for the existence of dark matter, but no detection that would reveal its particle nature. The possibility that what we observe as dark matter might actually be a modification of gravity rather than a new form of matter has also been explored. Various proposals, collectively known as modified gravity theories, attempt to explain the flat rotation curves of galaxies without invoking invisible matter. Mordechai-Milgram's modified Newtonian dynamics, often abbreviated as AMOND, is the most well-known of these. Mond proposes that the laws of gravity behave differently at very low accelerations, such as those found in the outer regions of galaxies, in a way that mimics the effects of dark matter. The proposal has had some empirical success in fitting individual galaxy rotation curves, but it faces significant challenges when applied to clusters of galaxies and to the cosmic microwave background. The mainstream view remains that dark matter is a real component of the universe, but the alternatives continue to be explored as a check on the standard assumptions. The rotation of galaxies on the largest observable scales connects to questions about the overall structure of the cosmos. The universe contains not just isolated galaxies, but also clusters, superclusters, filaments, and voids, organized into a vast cosmic web that spans the observable universe. Galaxies are not distributed randomly within this web, but are concentrated along the filaments that connect denser nodes. The rotation of galaxies appears to be related to their position within this larger structure. Galaxies near filaments tend to have rotation axes aligned with the filaments, while galaxies in clusters often have more random orientations. These alignments, although subtle, provide additional clues to the conditions under which galaxies acquired their angular momentum in the early universe. The detection of these alignments has been challenging, requiring large surveys of many galaxies and careful statistical analysis. The Sloan Digital Sky Survey, the Dark Energy Survey, and other large observational programs have produced datasets large enough to detect the subtle correlations between galaxy orientations and the surrounding cosmic structure. The results have been broadly consistent with theoretical predictions, supporting the idea that angular momentum on the largest scales is connected to the gravitational evolution of structure in the early universe. The picture that emerges is one in which the rotational properties of galaxies are not isolated features of individual systems, but are part of a larger pattern that reflects the entire history of cosmic structure formation. The role of dark matter in the formation of structure goes beyond simply providing additional gravitational mass. Dark matter also influences the timing and nature of structure formation in important ways. Because dark matter does not interact with light, it could begin to collapse gravitationally as soon as the universe became cool enough for matter to dominate over radiation. Ordinary matter, by contrast, was prevented from collapsing as long as it was strongly coupled to radiation, which happens until about 400,000 years after the Big Bang. The earlier collapse of dark matter created the gravitational potential wells into which ordinary matter later fell, accelerating the formation of structure. Without dark matter, the universe might never have produced the variety of structures we observe, including the galaxies whose rotation we have been discussing. The connection between dark matter and galactic rotation thus extends throughout the history of the cosmos. The angular momentum of galaxies is acquired during their formation, influenced by tidal torques from surrounding structures, modified by interactions with neighboring galaxies, and ultimately expressed as the rotation curves measured today. At every stage, dark matter plays a role, providing the dominant gravitational structure within which the visible processes unfold. Understanding rotation therefore requires understanding dark matter, and understanding dark matter has become inseparable from the broader project of understanding the cosmos. The implications extend even to questions about whether we have correctly identified all the relevant ingredients of the universe. The accumulated evidence for dark matter is overwhelming, but its particle nature remains unknown. Some have suggested that dark matter might consist not of a single type of particle, but of a more complex hidden sector with its own internal forces and structures. Such a hidden sector could have its own dynamics, potentially even its own forms of rotation and structure that we cannot directly observe, but that might leave subtle imprints on the visible universe. While these ideas remain speculative, they illustrate how deeply rotation and the search for dark matter are connected to fundamental questions about what the universe is made of. What is clear is that rotation, observed across all scales from the smallest galaxies to the largest cosmic structures, points to the existence and importance of dark matter. The rotation curves that puzzled astronomers in the 1970s have become a foundational pillar of modern cosmology. The continuing investigation of these curves and of their relationship to the broader cosmic structure remains central to the effort to understand the universe as a whole. Yet the same investigations also force a deeper reconsideration of what rotation itself really is. At the largest scales, we describe rotation in terms of orbital motions and angular momentum, but at the smallest scales, the concept of rotation takes on a different meaning. Particles possess intrinsic angular momentum that has no classical equivalent, a property whose discovery and explanation reshaped the foundations of physics in the early 20th century. The concept of spin acquires a strange new meaning when we descend to the scale of fundamental particles. At the level of electrons, protons, neutrons, and quarks, rotation is no longer a matter of objects literally turning in space. Instead, it becomes an intrinsic property, a quantum number that each particle carries as part of its fundamental identity. This property, called quantum spin, behaves mathematically like angular momentum, contributing to the total angular momentum of any system in which the particle participates, but its physical interpretation defies the analogies that work for macroscopic rotating objects. Understanding quantum spin is one of the most important achievements of 20th century physics, and it has consequences that reach into every aspect of how matter is structured and how it behaves. The discovery of quantum spin emerged from experimental puzzles in the early 20th century. Spectroscopists studying the light emitted and absorbed by atoms had found patterns that could not be explained by treating electrons as classical particles orbiting the nucleus. Certain spectral lines appeared in doublets where theory predicted single lines, and the splitting of these lines in magnetic fields showed patterns inconsistent with a simple picture of orbital motion. Various proposals were made to explain these anomalies, but progress was slow. The crucial breakthrough came in 1925 when two young Dutch physicists, Samuel Goudsmit and George Uhlenbeck, proposed that the electron possessed an intrinsic angular momentum independent of its orbital motion. They initially imagined this as a literal rotation of the electron about its own axis, but the magnitude required to fit the observations was incompatible with any classical picture. The surface of an electron, if treated as a small sphere, would have to be moving faster than the speed of light to produce the observed magnetic moment. Something more fundamental was at work. The mathematical framework for quantum spin was developed by Wolfgang Pauli and others over the following years. Pauli formulated a description in which spin was treated as a new quantum degree of freedom with no classical counterpart. The English physicist Paul Dirac then produced a relativistic equation for the electron in 1928 that automatically incorporated spin as a natural consequence of combining quantum mechanics with special relativity. The Dirac equation predicted the magnetic moment of the electron with remarkable accuracy and revealed that spin was not an arbitrary addition to quantum mechanics, but a deep feature of the structure of physical law. The same equation also predicted the existence of antimatter, with positrons being identified experimentally a few years later. The success of the Dirac equation cemented the status of spin as a fundamental property of nature. The values that spin can take are constrained in remarkable ways. The total spin of any particle, measured in units of the reduced Planck constant, must be either an integer or a half-integer. There are no in-between values. Photons, the particles of light, have spin 1. The hypothetical graviton, the carrier of gravity if gravity proves to have a quantum description, would have spin 2. The Higgs boson, discovered in 2012, has spin 0, making it a scalar particle with no orientation in space. Electrons, protons, and neutrons all have spin 1/2. Various other particles in the Standard Model fill out the picture, with each kind of particle having a definite spin value determined by its fundamental nature. The distinction between integer and half-integer spin has far-reaching consequences. Particles with integer spin are called bosons, and they obey statistical rules first formulated by Albert Einstein and Satyendra Nath Bose. Bosons can crowd into the same quantum state without limit. When many bosons share the same state, they can produce collective phenomena that have no equivalent in classical physics. The most familiar example is laser light, in which many photons occupy the same quantum mode, producing coherent radiation with properties unlike ordinary light. Another example is Bose-Einstein condensation, a state of matter that occurs when bosons at very low temperatures collapse into a single shared quantum state. The condensate behaves as a single quantum object on a macroscopic scale, exhibiting interference patterns and other quantum effects that are normally hidden at everyday scales. Particles with half-integer spin are called fermions, and they obey rules formulated by Enrico Fermi and Dirac. Fermions are subject to the exclusion principle articulated by Wolfgang Pauli, which states that no two identical fermions can occupy the same quantum state at the same time. This restriction has profound consequences for the structure of matter. Electrons in atoms cannot all collapse into the lowest energy state. Instead, they must fill successive states with different quantum numbers, building up the structure of electron shells around the nucleus. The detailed arrangement of these shells determines the chemical properties of the elements, leading to the patterns seen in the periodic table. The very existence of distinct elements with different properties, and therefore the existence of chemistry and all the structures that depend on chemistry, traces back to the spin property of electrons. The exclusion principle has consequences beyond the structure of atoms. In ordinary matter, when atoms are pressed together, the electrons in neighboring atoms cannot occupy the same quantum states. This produces an effective pressure that resists compression, called electron degeneracy pressure. The everyday rigidity of solid matter, the fact that solid objects do not pass through each other or collapse spontaneously, is ultimately due to this quantum mechanical effect rooted in the spin of electrons. Without the exclusion principle, all electrons could fall into the lowest energy state, and matter as we know it would not exist. The solidity of the world around us is a direct consequence of the half-integer spin of electrons. In more extreme conditions, electron degeneracy pressure plays an even more dramatic role. White dwarf stars, the remnants of stars like the Sun after they have exhausted their nuclear fuel, are supported against gravitational collapse entirely by the degeneracy pressure of their electrons. A white dwarf packs the mass of a star into a volume comparable to that of the Earth, producing extraordinarily high densities at which quantum mechanical effects dominate. The same principle applies on a more extreme scale in neutron stars, where the degeneracy pressure of neutrons holds the object together against even stronger gravitational forces. The masses, sizes, and ultimate stability of these compact objects depend directly on the fermionic nature of the particles composing them, and therefore on the half-integer spin that defines fermions. The mathematical treatment of spin uses operators that act on the quantum state of a particle to extract information about its spin orientation. For a spin one-half particle like an electron, the spin can be measured along any chosen axis, and the result is always either positive one-half or negative one-half of the basic unit. There is no intermediate value. This discreteness of spin measurements is one of the most counterintuitive features of quantum mechanics. A spin one-half particle is sometimes said to have its spin pointing up or down along the measurement axis, but it cannot have its spin pointing partway up or partway down. The act of measurement forces the particle into one of the two allowed states, regardless of the orientation it might have had before measurement. This binary nature of spin measurement leads to remarkable consequences when multiple particles are considered together. Two electrons can be combined into a singlet state in which their spins are perfectly anti-correlated. If one is measured to have spin up, the other must be measured to have spin down, and vice versa. This correlation persists even when the two electrons are separated by large distances, as long as nothing disturbs their quantum state. The phenomenon, called quantum entanglement, was the subject of intense debate among physicists in the 20th century. Einstein famously found it disturbing and referred to it as spooky action at a distance, suggesting that some additional hidden information must be carried by the particles to produce the observed correlations. But experimental tests, most decisively the Bell test experiments, performed beginning in the 1970s and continuing to the present day, have shown that no such hidden variables can explain the correlations. The entanglement of spins is a genuine feature of quantum reality with no classical analog. The technological applications of quantum spin have proliferated as our understanding has deepened. Magnetic resonance imaging, used routinely in medical diagnostics, relies on the spin of hydrogen nuclei in the body. When placed in a strong magnetic field, these nuclei align with the field and can be manipulated using radio frequency pulses. The resulting signals provide detailed images of soft tissues, revolutionizing medical care. The technique would not be possible without an understanding of nuclear spin and the methods for manipulating it. Similar principles underlie nuclear magnetic resonance spectroscopy used in chemistry, electron spin resonance used in materials science, and quantum computing technologies under intensive development. The manipulation of spin is at the heart of many emerging technologies, with potential applications ranging from secure communications to drug discovery. The fundamental nature of spin has also led to deep theoretical investigations of its origin. Why does spin have the values it has? Why are some particles bosons and others fermions? Modern theoretical physics offers some answers, but the picture remains incomplete. The spin statistics theorem, derived from the principles of relativistic quantum field theory, proves that integer spin particles must be bosons, and half-integer spin particles must be fermions, but it does not explain why these particular spin values exist in nature. The standard model of particle physics provides a catalog of particles with their spin values, but it does not derive these values from deeper principles. Various extensions of the standard model, including supersymmetry, attempt to provide such deeper connections by relating bosons and fermions to each other through a fundamental symmetry. Whether any of these extensions correctly describes the structure of nature remains an open question, with experimental searches ongoing at particle accelerators around the world. Spin connects to other aspects of fundamental physics in surprising ways. The behavior of spinning particles in curved spacetime, near rotating black holes, or in the very early universe leads to predictions that test the interface between quantum mechanics and general relativity. The angular momentum of photons, despite the fact that photons are massless, leads to effects called spin-orbit coupling that have been exploited in optical technologies. The spin of neutrinos, which interact only through the weak nuclear force, has played a critical role in the discovery that neutrinos have mass and oscillate between different flavors. Across the landscape of modern physics, spin continues to be a property that links many distinct phenomena and provides essential clues to the underlying structure of nature. What ties all of these observations together is the fundamental status of spin as a property of matter. Spin is not derived from anything more basic. It is one of the irreducible features that define what particles are. An electron is characterized by its mass, its electric charge, and its spin. Change any of these properties, and the particle becomes something different. The consistency with which spin appears in all physical theories, and the precision with which its consequences match experimental observations, makes it one of the best-tested concepts in science. And yet, despite this extensive understanding, the deeper question of why spin exists at all remains philosophically unsettled. We can describe what spin does and predict its effects with extraordinary accuracy, but the question of why nature should be organized around this particular property continues to invite reflection. The answer may lie not in any single mechanism, but in the very nature of how the universe builds its largest and smallest structures, beginning from the moments after its own birth.